Hi everyone, my name is Ava. I'm a lecturer and organizer for Success 191, and welcome to Lecture 2, which is going to focus on deep sequence modeling. So in the first lecture with Alexander, we learned about the essentials of neural networks and built up that understanding moving from perceptrons to feed-forward models. Next, we're going to turn our attention to applying neural networks to problems which involve sequential processing of data. And we'll see why these sorts of tasks require a different type of network architecture from what we've seen so far. To build up an understanding of these types of models, we're going to walk through this step by step, starting from intuition about how these networks work and building that up using where we left off with perceptrons and feed-forward models as introduced in the first lecture. So let's dive right in. To first, I'd like to motivate what we mean in terms of sequential modeling and sequential processing by beginning with a very simple, intuitive example. Let's suppose we have this picture here of a ball, and our task is to predict where it's going to travel to next. Without any prior information about the ball's history or understanding of the dynamics of its motion, any guess on its next position is going to be exactly that, just a guess. But instead, if in addition to the current location of the ball, I also gave you its previous locations, now our problem becomes much easier. And I think we can all agree that we have a sense of where the ball is going to travel to next. So hopefully this intuitive example gives you a sense of what we mean in terms of sequential modeling and sequential prediction. And the truth is that sequential data and these types of problems are really all around us. For example, audio like the waveform from my speech can be split up into a sequence of sound waves. And text can be split up into a sequence of characters or also words, where in here, each of these individual characters or each of the individual words can be thought of as a time step in our sequence. Now, beyond these two examples, there are many more cases in which sequential processing can be useful, from medical signals to EKGs, to prediction of stock prices, to genomic or genetic data, and beyond. So now that we've gotten a sense of what sequential data looks like, let's think about some concrete applications in which sequence modeling plays out in the real world. In the first lecture, Alexander introduced feed-forward models that sort of operate in this one-to-one manner, going from a fixed and static input to a fixed and static output. For example, he gave this use case of binary classification where we were trying to build a model that, given a single input of a student in this class, could be trained to predict whether or not that student was going to pass or not. And in this type of example, there's no time component. There's no inherent notion of sequence or of sequential data. When we consider sequence modeling, we now expand the range of possibilities to situations that can involve temporal inputs and also potentially sequential outputs as well. So for example, let's consider the case where we have a language processing problem where there's a sentence as input to our model. And that defines a sequence where the words in the sentence are the individual time steps in that sequence. And at the end, our task is to predict one output, which is going to be the sentiment or feeling associated with that sequence input. And you can think of this problem as having a sequence input, single output, or as sort of a many-to-one sequence problem. We can also consider the converse case, where now our input does not have that time dimension. So for example, when we're considering a static image, and our task is now to produce a sequence of outputs, for example, a sentence caption that describes the content in this image. And you can think of this as a one-to-many sequence modeling problem. Finally, we can also consider this situation of many-to-many, where we're now translating from a sequence to another sequence. And perhaps one of the most well-known examples of this type of application is in machine translation, where the goal is to train a model to translate sentences from one language to another. All right, so this hopefully gives you a concrete sense of use cases and applications where sequence modeling becomes important. Now, I'd like to move forward to understand how we can actually build neural networks to tackle these sorts of problems. And sometimes it can be a bit challenging to sort of wrap your head around how we can add this temporal dimension to our models. So to address this and to build up really a strong intuition, I want to start from the very fundamentals. And we'll do that by first revisiting the perceptron. And we're going to go step by step to develop a really solid understanding of what changes need to be made to our neural network architecture in order to be able to handle sequential data. All right, so let's recall and revisit the perceptron, which we studied in lecture 1. We define a set of inputs, right, which we can call x1 through xm. And each of these numbers are going to be multiplied by a weight matrix. And then they're going to all be added together to form this internal state of the perceptron, which we'll say is z. And then this value z is passed through a nonlinear activation function to produce a predictive output y hat. And remember that with the perceptron, you can have multiple inputs coming in. And since, in this lecture overall, we're considering sequence modeling, I'd like you to think of these inputs as being from a single time step in your sequence. We also saw how we could extend from this single perceptron to now a layer of perceptrons to yield multi-dimensional outputs. So for example, here we have a single layer of perceptrons in green, taking 3 inputs in blue and predicting 4 outputs shown in purple. But once again, does this have a notion of time or of sequence? No, it doesn't, because again, our inputs and our outputs you can think of as being from a fixed time step in our sequence. So let's simplify this diagram, right? And to do that, we'll collapse that hidden layer down to this green box, and our input and output vectors will be as depicted here. And again, our inputs, x, are going to be some vectors of length m, and our outputs are going to be of length n. But still, we're still considering the input at just a specific time, denoted here by t, which is nothing different from what we saw in the first lecture. And even with this simplified representation of a feed-forward network, we could naively already try to feed a sequence into this model by just applying that same model over and over again, once for each time step in our sequence. To get a sense of this, and how we could handle these individual inputs across different time steps, let's first just rotate this same diagram from the previous slide. So now again, we have an input vector x of t from some time step t, we feed it into our neural network, and then get an output vector at that time step. But since we're interested in sequential data, let's assume we don't just have a single time step, right? We have multiple individual time steps, which start from, let's say, time 0, the first time step in our sequence. And we could take that input at that time step, treat it as this isolated point in time, pass it into the model, and generate a predictive output. And we could do that for the next time step, again treating it as something isolated, and same for the next. And to emphasize here, all of these models depicted here are just replicas of each other, right? With different inputs at each of these different time steps. But we know sort of that our output, and we know from the first lecture that our output vector, y hat, at a particular time step t, is just going to be a function of the input at that time step. But let's take a step back here for a minute. If we're considering sequential data, it's probably very likely that the output, or the label, at a later time step is going to somehow depend on the inputs at prior time steps. So what we're missing here by treating these individual time steps as individual isolated time steps is this relationship that's inherent to sequence data between inputs earlier on in the sequence to what we predict later on in the sequence. So how could we address this? What we really need is a way to relate the computations and the operations that the network is doing at a particular time step to both the prior history of its computation from prior time steps, as well as the input at that time step, and finally to have a sense of forward-looking, right? To be able to pass that information, the current information, onto future time steps. So let's try to do exactly that. What we'll consider is linking the information and the computation of the network at different time steps to each other. Specifically, we're going to introduce this internal memory or cell state, which we denote here as h of t. And this is going to be this memory that's going to be maintained by the neurons and the network itself. And this state can be passed on time step to time step across time. And the key idea here is that by having this recurrence relation, we're capturing some notion of memory of what the sequence looked like. What this means is now the network's output predictions and its computations are not only a function of the input at a particular time step, but also the past memory of cell state, denoted by H. That is to say that our output depends on both our current inputs as well as the past computations and the past learning that occurred. And we can define this relationship via these functions that map inputs to output. And these functions are standard neural network operations that Alexander introduced in the first lecture. So once again, our output, our prediction, is going to depend not only on the current input at a particular time step, but also on the past memory. And because, as you see in this relation here, our output is now a function of both the current input and the past memory at a previous time step, this means we can describe these neurons via a recurrence relation, which means that we have the cell state that depends on the current input and again on the prior cell states. And the depiction on the right of this line shows these individual time steps being sort of unrolled across time. But we could also depict the same relationship by this cycle. And this is shown on the loop on the left of the slide, which shows this concept of a recurrence relation. And it's exactly this idea of recurrence that provides the intuition and the key operations behind recurrent neural networks, or RNNs. And we're going to continue for the remainder of this lecture to build up from this foundation and build up our understanding of the mathematics of these recurrence relations and the operations that define RNN behavior. All right, so let's formalize this a little bit more. The key idea here, as I mentioned, and hopefully that you take away from this lecture, is that these RNNs maintain this internal state, h of t, which is updated at each time step as the sequence is processed. And this is done via this recurrence relation, which specifically defines how the state is updated at the time step. Specifically, we define this internal cell state, h of t. And that internal cell state is going to be a function that is going to be defined by a function that can be parametrized by a set of weights w, which are what we're actually trying to learn over the course of training such a network. And that function, f of w, is going to take as input both the input at the current time step x of t, as well as the prior state, h of t minus 1. And how do we actually find and define this function? Again, it's going to be parametrized by a set of weights that are going to be specifically what's learned over the course of training the model. And a key feature of RNNs is that they use this very same function and this very same set of parameters at every time step of processing the sequence. And of course, the weights are going to change over time over the course of training, and later on we'll see exactly how, but at each iteration of training, that same set of weights is going to be applied to each of the individual time steps in the sequence. All right. So now let's step through the algorithm for updating RNNs to get a better sense of how these networks work. We're going to begin by initializing our network, which I'm just abstracting away here in this code block in the pseudocode block as RNN. And we're also going to initialize a hidden state as well as a sentence. And let's say our task here is to predict the next word in the sentence. The RNN algorithm is as follows. We're going to loop through the words in this sentence, and at each step, we're going to feed both the current word and the previous hidden state into our RNN. And this is going to generate a prediction for the next word, as well as an update to the hidden state itself. And finally, when we're done processing these 4 words in this sentence, we can generate our prediction for what the next word actually is by considering the RNN's output after all the individual words have been fed through the model. All right, so as you may have realized, the RNN computation includes both this internal cell state update to h of t, as well as the output prediction itself. So now we're going to concretely walk through how each of these computations is defined. All right, going from bottom to top, right? We're going to consider our input vector x of t, and we're next going to apply a function to update the hidden state. And this function is a standard neural network operation, just like we saw in the first lecture. And again, because this internal cell state h of t is going to depend on both the input x of t as well as the prior cell state h of t minus 1, we're going to multiply each of these individual terms by their respective weight matrices. And we're going to add the result and then apply a nonlinear activation function, which in this case is going to be a hyperbolic tangent, to the sum of these 2 terms to actually update the value of the hidden state. And then, to generate our output at a given time step, we take that internal hidden state, multiply it by a separate weight matrix, which inherently produces a modified version of this internal state. And this actually forms our output prediction. So this gives you the mathematics behind how the RNN can actually update its hidden state and also to produce a predictive output. All right, so far we've seen RNNs being depicted as having these internal loops that feed back on themselves. And we've also seen how we can represent this loop as being unrolled across time, where we can start from a first time step and continue to unroll the network across time, up until time step t. And within this diagram, we can also make explicit the weight matrices, starting from the weight matrix that defines how the inputs at each time step are being transformed in the hidden state computation, as well as the weight matrices that define the relationship between the prior hidden state and the current hidden state, and finally, the weight matrix that transforms the hidden state to the output at a particular time step. And again, to reemphasize, in all of these cases, for all of these weight matrices, we're going to be reusing the same weight matrices at every time step in our sequence. Now, when we make a forward pass through the network, we're going to generate outputs at each of those individual time steps. And from those individual outputs, we can derive a value for the loss. And then we can sum all of these losses from the individual time steps together to determine the total loss, which will be ultimately what is used to train our RNN. And we'll get to exactly how we achieve this in a few slides. All right. So now this gives you an intuition and mathematical foundation for how we actually can make a forward pass, a forward step through our RNN. Let's now walk through an example of how we can implement an RNN from scratch using TensorFlow. We're going to define the RNN using a layer, so we can build it up from as inheriting from the layer class that Alexander introduced in the first lecture. We can also initialize the weight matrices and also finally initialize the hidden state of the RNN to all zeros. Our next step is going to be to define what we call the call function. And this function is really important because it describes exactly how we can make a forward pass through the network given a input. Our first step in this forward pass is going to be to update the hidden state, according to that same exact equation we saw earlier, where the hidden state and from the previous time step and an input x are multiplied by their relevant weight matrices, are summed, and then passed through a nonlinear activation function. We next compute the output by transforming this hidden state via multiplication by a separate weight matrix, And at each time step, we're going to return both the current output as well as the hidden state. So this gives a sense of, breaks down how we define the forward pass to an RNN in code using TensorFlow. But conveniently, TensorFlow has already implemented these types of RNN cells for us, which you can use via the simple RNN layer. And you're going to get some practice doing exactly this and using the RNNs later on in today's lab. All right, so to recap, now that we're at this point in this lecture where we've built up our understanding of RNNs and their mathematical basis, I'd like to turn back to those applications of sequence modeling that we discussed earlier on. And hopefully now you've gotten a sense of why RNNs can be particularly suited for handling sequential data. Again, with feed-forward or traditional neural networks, we're operating in this one-to-one manner, going from a static input to a static output. In contrast, with sequences, we can go from a sequential input, where we have many time steps defined sequentially over time, feed them into a recurrent neural network, and generate a single output, like a classification of sentiment or emotion associated with a sentence. We can also move from a static input, for example, an image, to a sequential output, going from one to many. And finally, we can go from sequential input to sequential output, many to many. And two examples of this are in machine translation and also in music generation. And with the latter, with music generation, you'll actually get the chance to implement an RNN that does exactly this later on in today's lab. Beyond this, we can extend recurrent neural networks to many other applications in which sequential processing and sequential modeling may be useful. To really appreciate why recurrent neural networks are so powerful, I'd like to sort of consider a concrete set of what I like to call design criteria that we need to be keeping in mind when thinking about sequence modeling problems. Specifically, we need to be able to ensure that our recurrent neural network, or any machine learning model that we may be interested in, will be equipped to handle variable length sequences. Because not all sentences, not all sequences are going to have the same length. So we need to have the ability to handle this variability. We also need to have this critical property of being able to track long-term dependencies in the data and to have a notion of memory. And associated with that is also the ability to have this sense of order and have a sense of how things that occur previously or earlier on in the sequence affect what's going to happen or occur later on. And to do this, we can achieve both points 2 and 3 by using weight sharing and actually sharing the values of the weight matrices across the entire sequence. And we'll see, I'm telling you now, and we'll see that recurrent neural networks do indeed meet all these sequence modeling design criteria. All right, so to understand these criteria concretely, I'd like to consider a very concrete sequence modeling problem, which is going to be the following. Given some series of words in a sentence, our task is going to be to predict the most likely next word to occur in that sentence. All right, so let's suppose we have this sentence as an example. This morning, I took my cat for a walk. And our task is, let's say, we're given these words, this morning I took my cat for a, and we want to predict the next word in the sentence, walk. And our goal is going to be to try to build a recurrent neural network to do exactly this. What's our first step to tackle this problem? Well, the first consideration before we even get started with training our model is how we can actually represent language to a neural network. So let's suppose we have a model where we input the word deep, and we want to use the neural network to predict the next word, learning. What could be the issue here in terms of how we're passing in this input to our network? Remember that neural networks are functional operators. They execute functional mathematical operations on their inputs and generate numerical outputs as a result. So they can't really interpret and operate on words if they're just passed in as words. So what we have here is just simply not going to work. Instead, neural networks require numerical inputs that can be a vector or an array of numbers, such that the model can operate on them to generate a vector or array of numbers as the output. So this is going to work for us, but operating just on words simply is not. All right, so now we know that we need to have a way to transform language into this vector or array-based representation. How exactly are we going to go about this? The solution we're going to consider is this concept of embedding, which is this idea of transforming a set of identifiers for objects, effectively indices, into a vector of fixed size that captures the content of the input. So to think through how we could actually go about doing this for language data, let's again turn back to that example sentence that we've been considering. This morning I took my cat for a walk. We want to be able to map any word that appears or could appear in our body of language to a fixed size vector. So our first step is going to be to generate a vocabulary, which is going to consist of all unique words in our set of language. We can then index these individual words by mapping individual unique words to unique indices. And these indices can then be mapped to a vector embedding. One way we could do this is by generating sparse and binary vectors that are going to have a length that's equal to the number of unique words in our vocabulary, such that we can then indicate the nature of a particular word by encoding this in the corresponding index. So for example, for the word cat, we could encode this at the second index in this sparse binary vector. And this is a very common way of embedding and encoding language data, and it's called a one-hot encoding. And very likely you're going to encounter this in your journey through machine learning and deep learning. Another way we could build up these embeddings is by actually learning them. So the idea here is to take our index mapping and feed that index mapping into a model, like a neural network model, such that we can then transform that index mapping across all the words of our vocabulary to a vector of a lower dimensional space where the values of that vector are learned, such that words that are similar to each other have similar embeddings. And an example that demonstrates this concept is shown here. All right, so these are two distinct ways in which we can encode language data and transform language data into a vector representation that's going to be suitable for input to a neural network. Now that we've built up this way to encode language data and to actually get started with feeding it into our recurrent neural network model, let's go back to that set of design criteria, where the first capability we desired is this ability to handle variable sequence lengths. And again, let's consider this task of trying to predict the next word in a sentence. We could have very short sentences, right, where driving the meaning of our prediction are going to be very close to each other. But we could also have a longer sequence or an even longer sequence where the information that's needed to predict the next word occurs much earlier on. And the key requirement for our recurrent neural network model is the ability to handle these inputs of varying length. Feed-forward networks are not able to do this because they have inputs of fixed dimensionality. And then those fixed dimensionality inputs are passed into the next layer. In contrast, RNNs are able to handle variable sequence lengths. And that's because those differences in sequence lengths are just differences in the number of time steps that are going to be input and processed by the RNN. So RNNs meet this first design criterion. Our second criterion is the ability to effectively capture and model long-term dependencies in data. And this is really exemplified in examples like this one, where we clearly need information from much earlier in the sequence or the sentence to accurately make our prediction. RNNs are able to achieve this because they have this way of updating their internal cell state via the recurrence relation we previously discussed, which fundamentally incorporates information from the past state into the cell state update. So this criteria is also met. Next, we need to be able to capture differences in sequence order, which could result in differences in the overall meaning or property of a sequence. For example, in this case, where we have two sentences that have opposite semantic meaning but have the same words with the same counts, just in a different order. And once again, the cell state maintained by an RNN depends on its past history, which helps us capture these sorts of differences because we are maintaining information about past history and also reusing the same weight matrices across each of the individual time steps in our sequence. So hopefully going through this example of predicting the next word in a sentence with a very particularly common type of sequential data being language data, this shows you how sequential data more broadly can be represented and encoded for input to RNNs, and how RNNs can achieve the set of sequence modeling design criteria. All right, so now at this stage in the lecture, we've built up our intuition and our understanding of how recurrent neural networks work, how they operate, and what it means to model sequences. Now we can discuss the algorithm for how we can actually train recurrent neural networks. And it's a twist on the backpropagation algorithm that was introduced in lecture 1. It's called backpropagation through time. So to get there, let's first, again, take a step back to our first lecture and recall how we can actually train feed-forward models using the backpropagation algorithm. We first take a set of inputs and make a forward pass through the network, going from input to output. And then to train the model, we backpropagate gradients back through the network. And we take the derivative of the loss with respect to each weight parameter in our network, and then adjust the parameters, the weights in our model, in order to minimize that loss. For RNNs, as we walked through earlier, our forward pass through the network consists of going forward across time and updating the cell state based on the input as well as the previous state, generating an output, and fundamentally computing the loss values at the individual time steps in our sequence, and finally summing those individual losses to get the total loss. Instead of backpropagating errors through a single feed-forward network at a single time step, in RNNs, those errors are going to be backpropagated from the overall loss through each individual time step, and then across the time steps, all the way from where we are currently in the sequence back to the beginning. And this is the reason why it's called backpropagation through time. Because as you can see, all of the errors are going to be flowing back in time from the most recent time step to the very beginning of the sequence. Now, if we expand this out and take a closer look at how gradients can actually flow across this chain of repeating recurrent neural network module, we can see that between each time step, we have to perform this matrix multiplication that involves the weight matrix W, H of H. And so computing the gradient with respect to the initial cell state, H of 0, is going to involve many factors of this weight matrix and also repeated computation of the gradients with respect to this weight matrix. This can be problematic for a couple of reasons. The first being that if we have many values in this series, this chain of matrix multiplications, where the gradient values are greater than 1, or the weight values are greater than 1, we can run into a problem that's called the exploding gradient problem, where our gradients are going to become extremely large and we can't really optimize. And a solution here is to do what is called gradient clipping, effectively scaling back the values of particularly large gradients to try to mitigate this. We can also have the opposite problem, where now our weight values or our gradients are very, very small. And this can lead to what is called the vanishing gradient problem, when gradients become increasingly smaller and smaller and smaller, such that we can no longer effectively train the network. And today we're going to discuss 3 ways in which we can address this vanishing gradient problem. First, by cleverly choosing our activation function, also by smartly initializing our weight matrices, and finally, we'll discuss how we can make some changes to the network architecture itself to alleviate this vanishing gradient problem. All right, in order to get into that, you'll need some intuition about why vanishing gradients could be a problem. Let's imagine you keep multiplying a small number, something in between 0 and 1, by another small number. Over time, that number is going to keep shrinking and shrinking, and eventually it's going to vanish. And what this means when this occurs for gradients is that it's going to be harder and harder and harder to propagate errors from our loss function back into the distant past, because we have this problem of the gradients becoming smaller and smaller and smaller. And ultimately what this will lead to is we're going to end up biasing the weights and the parameters of our network to capture shorter-term dependencies in the data rather than longer-term dependencies. To see why this could be a problem, let's again consider this example of training a language model to predict the next word in a sentence of words. And let's say we're given this phrase, "the clouds are in the blank." In this case, it's pretty obvious what the next word is likely going to be, right? Sky. Because there's not that much of a gap in the sequence between the relevant information, the word cloud, and the place where our prediction is actually going to be needed. And so an RNN could be equipped to handle that. But let's say now we have this other sentence, "I grew up in France and I speak fluent blank," where now there's more context that's needed from earlier in the sentence to make that prediction. And in many cases, that's going to be exactly the problem, where we have this large gap between what's relevant and the point where we may need to make a prediction. And as this gap grows, standard RNNs become increasingly unable to connect the relevant information. And that's because of this vanishing gradient problem. So it relates back to this need to be able to effectively model and capture long-term dependencies in data. How can we get around this? The first trick we're going to consider is pretty simple. We can smartly select the activation function our networks use. Specifically, what is commonly done is to use a ReLU activation function, where the derivative of this activation function is greater than 1 for all instances in which x is greater than 0. And this helps the value of the gradient of our with respect to our loss function to actually shrink when the values of its input are greater than 0. Another thing we can do is to be smart in how we actually initialize the parameters in our network. And we can specifically initialize the weights to the identity matrix to be able to try to prevent them from shrinking to 0 completely and very rapidly during backpropagation. Our final solution, and the one that we're going to spend the most time discussing, and it's also the most robust, is to introduce and to use a sort of more complex recurrent unit that can more effectively track long-term dependencies in the data by, intuitively, you can think of it as controlling what information is passed through and what information is used to update the actual cell state. Specifically, we're going to use what is called gated cells. And today we're going to focus on one particular type of gated cell, which is definitely the most common and most broadly used in recurrent neural networks. And that's called the long short-term memory unit, or LSTM. And what's cool about LSTMs is that networks that are built using LSTMs are particularly well-suited at better maintaining long-term dependencies in the data and tracking information across multiple time steps to try to overcome this vanishing gradient problem, and more importantly, to more effectively model sequential data. All right, so LSTMs are really the workhorse of the deep learning community for most sequential modeling tasks. So let's discuss a bit about how LSTMs work. And my goal for this part of the lecture is to provide you with the intuition about the fundamental operations of LSTMs, abstracting away a little bit of the math because it can get, again, a little confusing to wrap your mind around. But hopefully, I hope to provide you with the intuitive understanding about how these networks work. All right, so to understand the key operations that make LSTM special, let's first go back to the general structure of an RNN. And here I'm depicting it slightly differently, but the concept is exactly that from what I introduced previously, where we build up our recurrent neural network via this repeating module linked across time. And what you're looking at here is a representation of an RNN that shows an illustration of those operations that define the state and output update functions. So here we've simplified it down, where these black lines effectively capture weight matrix multiplications, and the yellow rectangles, such as the tan H depicted here, show the application of a nonlinear activation function. So here in this diagram, this repeating module of the RNN contains a single neural network computation node, which is consisting of a tan H activation function layer. So here, again, we perform this update to the internal cell state h of t, which is going to depend on the previous cell state h of t minus 1, as well as the current input x of t. And at each time step, we're also going to generate an output prediction y of t, a transformation of the state. LSTMs also have this chain-like structure, but the internal repeating module, that recurrent unit, is slightly more complex. In an LSTM, this repeating recurrent unit contains these different interacting layers, again, which are defined by standard neural network operations like sigmoid and tan H nonlinear activation functions, weight matrix multiplications. But what's cool and what's neat about these different interacting layers is that they can effectively control the flow of information through the LSTM cell. And we're going to walk through how these updates actually enable the LSTMs to track and store information throughout many time steps. And here you can see how we can define a LSTM layer using TensorFlow. All right, so the key idea behind LSTMs is that they can effectively selectively add or remove information to the internal cell state using these structures that are abstracted away by being called gates. And these gates consist of a standard neural network layer, like a sigmoid, shown here, and a pointwise multiplication. So let's take a moment to think about what a gate like this could be doing. In this case, because we have the sigmoid activation function, this is going to force anything that passes through that gate to be between 0 and 1. So you can effectively think of this as modulating and capturing how much of the input should be passed through, between nothing, 0, or everything, 1, which effectively gates the flow of information. LSTMs use this type of operation to process information by first forgetting irrelevant history, secondly by storing the most relevant new information, thirdly by updating their internal cell state and then generating a output. The first step is to forget irrelevant parts of the previous state, and this is achieved by taking the previous state and passing it through one of these sigmoid gates, which again, you can think of it as modulating how much should be passed in or kept out. The next step is to determine what part of the new information and what part of the old information is relevant, and to store this into the cell state. And What is really critical about LSTMs is that they maintain the separate value of the cell state, C of t, in addition to what we introduced previously, H of t. And C of t is what is going to be selectively updated by via these gate-wise operations. Finally, we can return an output from our LSTM. And so there's a interacting layer, an output gate, that can control what information that's encoded in the cell state is ultimately outputted and sent to the network as input in the following time step. So this operation controls both the value of the output, y of t, as well as the cell state that's passed on time step to time step in the form of h of t. The key takeaway that I want you to have about LSTMs from this lecture is that they can regulate information flow and storage. And by doing this, they can effectively better capture longer-term dependencies and also help us train the networks overall and overcome the vanishing gradient problem. And the key way that they help during training is that all of these different gating mechanisms actually work to allow for what I like to call the uninterrupted flow of gradient computation over time. And this is done by maintaining this separate cell state, C of t, across which the actual gradient computation, so taking the derivative with respect to the weights, updating derivative of the loss with respect to the weights, and shifting the weights in response, occurs with respect to this separately maintained cell state, C of t. And what this ultimately allows for is that we can mitigate the vanishing gradient problem that's seen with traditional RNNs. So to recap on the key concepts behind LSTMs. LSTMs maintain a separate cell state from what is outputted, that's C of t. They use these gates to control the flow of information by forgetting irrelevant information from past history, storing relevant information from the current input, updating their cell state, and outputting the prediction at each time step. And it's really this maintenance of the separate cell state, C of t, which allows for backpropagation through time with uninterrupted gradient flow and more efficient and more effective training. And so for these reasons, LSTMs are very, very commonly used as sort of the backbone RNN in modern deep learning. All right. So now that we've gone through the fundamental workings of RNNs, been introduced to the backpropagation through time algorithm, and also considered the LSTM architecture, I'd like to consider a few very concrete practical examples of how recurrent neural networks can be deployed for sequential modeling, including an example that you'll get experience with in today's lab. And that's the task and the question of music generation or music prediction. So let's suppose you're trying to build up a recurrent neural network that can take sequences of musical notes and actually, from that sequence, predict what is the most likely next note to occur. And not only do you want to predict what's the most likely next note to occur, we want to actually take this trained model and use it to generate brand new musical sequences that have never been heard before. And we can do this by basically seeding a trained RNN model with a first note, and then iteratively building up the sequence over time to generate a new song. And indeed, this is one of the most exciting and powerful applications of recurrent neural networks. And to motivate this, which is going to be the topic of your lab today, I'm going to introduce a really fun and interesting historical example. And it turns out that one of the most famous classical composers, Franz Schubert, had a famous symphony which was called the Unfinished Symphony. And the symphony is described exactly like that. It's unfinished. It was actually left at 2 movements rather than 4, and Schubert was not able to finish composing the symphony before he died. And recently, there was a neural network-based algorithm that was trained and put to the test to actually finish this symphony and compose 2 new movements. And this was done by training the model, a recurrent neural network model, on Schubert's body of work, and then testing it by tasking the model with trying to generate the new composition given the score of the previous two movements of this unfinished symphony. So let's listen in to see what the result was. I'd like to continue because I'm actually enjoying listening to that music, but we also have to go on with the lecture. So pretty awesome, right? And I hope you agree that I think, it's really exciting to see neural networks being put to the test here, but also, at least for me, this sparks some questioning and understanding about sort of what is the line between artificial intelligence and human creativity. And you'll get a chance to explore this in today's lab. Another cool example is beyond music generation is one in language processing, where we can go from an input sequence, like a sentence, to a single output, where we can train an RNN to let's say, produce a prediction of emotion or sentiment associated with a particular sentence, either positive or negative. And this is effectively a classification task, much like what we saw in the first lecture, except again, we're operating over a sequence where we have this time component. So because this is a classification problem, we can train these networks using a cross-entropy loss. And one application that we may be interested in is classifying the sentiments associated with tweets. So for example, this tweet, we could train an RNN to predict that this first tweet about our class, 6S191, has a positive sentiment, but that this other tweet about the weather actually has a negative sentiment. All right, so the next example I'll talk about is one of the most powerful applications of recurrent neural networks, and it's the backbone of things like Google Translate. And that's this idea of machine translation, where our goal is to input a sentence in one language and train an RNN to output a sentence in another language. And this can be done by having an encoder component, which effectively encodes the original sentence into some state vector, and a decoder component, which decodes that state vector into the target language, the new language. But it's quite remarkable that using the foundations and the concepts that we learned today about sequential modeling and about recurrent neural networks, we can tackle this very complex problem of machine translation. But what could be some potential issues with using this approach, using RNNs or LSTMs? The first issue is that we have this encoding bottleneck. Which means that we need to encode a lot of content, for example, a long body of text of many different words, into the single memory state vector, which is a compressed version of all the information necessary to complete the translation. And it's this state vector that's ultimately going to be passed on and decoded to actually achieve the translation. And by forcing this compression, we could actually lose some important information by imposing this extreme encoding bottleneck, which is definitely a problem. Another limitation is that the recurrent neural networks that we learned about today are not really that efficient, as they require sequential processing of information, which is the point that I've sort of been driving home all along. And it's this sequential nature that makes these recurrent neural networks relatively inefficient on modern GPU hardware because it's difficult to parallelize them. And furthermore, besides this problem of speed, we need to be able to train the RNN. We need to go from the decoded output all the way back to the original input, which will involve going through order t, or number t iterations of the network, where t is the number of time steps that we feed into our sequence. And so what this means in practice is that backpropagation through time is actually very, very expensive, especially when considering large bodies of text that need to be translated. That's depicted here. Finally, and perhaps most importantly, is this fact that traditional RNNs have limited memory capacity. And we saw that recurrent neural networks suffered from this vanishing gradient problem. LSTMs helped us a bit, but still, both of these architectures are not super effective at handling very long temporal dependencies that could be found in large bodies of text that need to be translated. So how can we build an architecture that could be aware of these dependencies that may occur in larger sequences or bodies of text? To overcome these limitations, a method that's called attention was developed. And the way it works is that instead of the decoder component having access to only the final encoded state, that state vector passed from encoder to decoder, instead, the decoder now has access to the states after each of the time steps in the original sentence. And it's the weighting of these vectors that is actually learned by the network over the course of training. And this is a really interesting idea because what this attention module actually does is to learn from the input which points and which states to attend to. And it makes it very efficient and capable of capturing long-term dependencies as easily as it does short-term dependencies. And that's because to train such a network, it only requires a single pass through this attention module, no backpropagation through time. And what you can think of these attention mechanisms as providing is this sort of learnable memory access. And indeed, this system is called attention because when the network is actually learning the weighting, it's learning to place its attention on different parts of the input sequence to effectively capture a sort of accessible memory across the entirety of the original sequence. It's a really, really, really powerful idea. And indeed, it's the basis of a new class and a rapidly emerging class of models that are extremely powerful for large-scale sequential modeling problems. And that class of models is called transformers, which you may have heard about as well. This application and this consideration of attention is very important not only in language modeling, but in other applications as well. So for example, if we're considering autonomous vehicles, at any moment in time, an autonomous vehicle like this one needs to have an understanding of not only where every object is in its environment, but also where a particular object may move in the future. So here's an example of a self-driving car. And the red boxes on the right-hand side depict a cyclist. And as you can see, the cyclist is approaching a stopped vehicle, shown here in purple. And the self-driving car, can be able to recognize that the cyclist is now going to merge in front of the car. And before it does so, the self-driving car pulls back and stops. And so this is an example of trajectory prediction and forecasting in which it's clear that we need to be able to attend to and make effective predictions about where dynamic objects in a scene may move to in the future. Another powerful example of sequential modeling is in environmental modeling and climate pattern analysis and prediction. So here we can visualize the predicted patterns for different environmental markers such as winds and humidity. And it's an extremely important and powerful application for sequence modeling and for recurrent neural networks because effectively predicting the future behavior of such markers could aid in projecting and planning for long-term climate impact. All right. So hopefully over the course of this lecture, you've gotten a sense of how recurrent neural networks work and why they're so powerful for processing sequential data. We saw how we can model sequences via this defined recurrence relation and how we could train them using the backpropagation through time algorithm. We then explored a bit about how gated cells like LSTMs could help us model long-term dependencies in data, and also discussed applications of RNNs to music generation, machine translation, and beyond. So with that, we're going to transition now to the lab sessions, where you're going to have a chance to begin to implement recurrent neural networks on your own using TensorFlow. And we encourage you to come to the class and the lab office hour Gather Town session to discuss the labs, ask your questions about both lab content as well as content from the lectures, and we look forward to seeing you there. Thank you.